Welcome to RIT-Sec. What is it, week 7, guys? It's week 7. We're about to go in spring break. 8? 8, dude. It's all blending in together now. We're going on spring break, though. This is the last meeting of the first half of the semester. Welcome to RIT-Sec, Security 3 Community. I'm Kenneth. Yeah. Announcements. Join the Discord. Please join the Discord. I would assume everyone in here is in the Discord, but if you're not, here's the QR code. Okay. Please sign in. Is the sign in up? Okay, I'll give you guys a few seconds to sign in. It's about to come up now. Okay, we'll go to the next slide now. Check the calendar. That's how you know when all our events are. Later half of the semester is going to be quite interesting, so keep up to date with that. There's a lot of stuff going on. Excuse me. Join the mailing list. You'll get those sweet, crafted weekly newsletters. Then you know what's going on if you don't see it in the Discord. Oh, yeah. Meet the sponsors. Clap it up, please. Did I update these? These should be updated. I think these are updated. I'm pretty sure these are updated. I just got scared. Yeah, follow our social media. Yeah. Sophia's going to be posting there soon. ISDS photos releasing very soon. Oh, yeah. Okay. Our single, external announcement is Contagion's Hack the Box Cyberpocalypse. They're doing it together. Saturday 18th, March 2022, starting at 1 p.m. What is that? UTC, forgot what that stands for. To Thursday 23rd, March 2023. 1 UTC, same thing. Scan the QR code, please. Let me know if that works or not, because Tenchi didn't give me the QR code. I had to generate this one. It'll be a fun time. You can CTF up with Contagion. It's a Google form. Yeah, it has details on it, I believe. Okay. Okay. Thank you, Braden, for your input. Did it not work? I wouldn't know. It's for a week, and you can do it, intermittently, you know. All right. So, it's my week. We're going to be talking about hardware. You're in for a very sweet treat. I would like to preface this is going to be a very casual presentation. Feel free to ask me questions. We're going to do this Wiggles style. So if you have not been to Wiggles, you're in for a good old time. Oh, yeah. Don't say, oh, no. It's, oh, yeah. So picture this. Who am I? Right. My name is Kenneth Anderson. I'm a DMV native. I'm a third-year CSEC major. The C minor is debatable. We're in rough times right now. I'm one of the quote-unquote leads for Wiggles, a.k.a. Ergo Burr. Just me and Braden heckling each other about wireless concepts. I have extensive field experience, some would say. I've done some red team stuff, some black team stuff, some blue team stuff. I have some plants, and I have fish. They keep me happy in my lonely apartment. And I am an avid enjoyer of Wes Anderson, and specifically Fantastic Mr. Fox. Yeah, there's my email and my Discord if you want to talk to me. But, yeah. Yep. Okay. So, what's going to be covered? I had to, do this. Transistors, logic gates, microcontrollers, and system on chips. Double EEPROM, flash storage briefly. Where is hardware used IRL? Like hardware embedded systems is kind of like, not a buzzword, but it gets thrown around so much. I'm just going to provide some examples of where, what are the applications of this stuff. Ethical circumvention of embedded device security implementations. What you guys pretty much came here for. And briefly, a little slide on TPM, because TPM is pretty rad. Trusted computing is pretty swag, too. And my little Guilfoyle meme. Yeah. Do I do I be honest or nice? Because that's what I battle with every day. Oh yeah. Questions, comments, concerns? No? Guys, please talk to me. What? Well, yeah, we're going to talk about that. Yeah. Like I said, it's very casual. There's no demo today, unfortunately, because I know, right? I'm sorry that I couldn't acquire all this hardware and bring you guys to a lab to experiment. Yeah, I'm sorry. Darn. Yeah. Okay. Thank you, Chase K. Okay. I would also like to preference I'm not an engineer. I'm not getting an engineering degree. I don't have the engineering title. I just fiddle and tinker around a little bit, and I have some experience doing embedded device security. So I guess I have the right to talk about it because I know a little more than you guys do. Um, this photo's cool. What? Yeah, feel free to screenshot or don't screenshot. So let me get a little sip of my water real quick. Hold up. Yeah, that's so real, bestie. Okay. So you may be asking yourself, Kenny, what is a transistor, right? Um, to be honest, I don't know. It's a lot of physics that go into this stuff. But pretty much, as Brad went over in the cloud computing talk beginning of this semester, I believe, computers are just rocks that they taught to think. So pretty much, we send a bunch of silicon. It's actually like the most, what is it, second most abundant resource on the planet, right next to oxygen, actually. We send some silicon to the foundry, the forge, or whatever, and we convert them to semiconductors, right? And then you may ask, Kenny, what are semiconductors? It's the point in between being conductive and non-conductive, and it's the perfect balance for being able to hold charges, right? And you may be asking yourself, Kenny, why would you need to have silicon hold a charge? Well, picture this. We need to store data. You think of a binary, right? Ones and zeros, right? What's another form of binary? On and off, right? If we can teach this rock to hold in a positive charge or no charge at all, we can start doing computations, as all of you are familiar with. I think, yeah, they teach you this in 140. I mean, you guys should know what binary is. If not, that's crazy. But yeah, like I said, semiconductors are the perfect balance between being conductive and non-conductive. And silicon is very important in producing these things called MOSFETs, metal oxide semiconductor field effective transistors, which are pretty swag. More specifically, though, these MOSFETs generally have two types, or 2 to 3 types, depending on how you label it. We have PMOS and NMOS. And all that really denotes is their state when a charge is applied and not applied. So what is it, if I remember correctly? Balls. If I remember correctly, negative NMOS or negative MOS are closed by default unless a charge is applied, and when a charge is applied, it opens. And PMOS is the inverse of it, so it's open by default, and when a charge is applied, it's closed. And that's like the basis of PMOS and NMOS transistors. But when you start combining these, you get CMOS, right? It's complementary, and you can combine them to do really cool things, as shown in this, right? This is how you draw an NMOS, PMOS, and CMOS. This is all going to build up on each other. And you may be asking, Kenny, how do these PMOS and NMOS transistors work? Physics, I'm not getting into that. It's a lot of weird, like passing electrons over substrate, and then there's like a well. But all you need to know is that all transistors have a gate, a source, and a drain. The source is the incoming power, the gate's the incoming data, I believe, and then the drain is the output, and that's kind of the 3 little prongs. It's been a while since I've actually had to recall this, so I apologize. But yeah, transistors are very important in the world of computing. You pretty much build everything using these. As shown here, we have a little AND gate. I assume you guys are familiar with AND gates. If not, we're going to go into them. But this is like the de facto logic gate, right? The AND gate is comprised of 2 PMOS transistors. Like, you can build anything with these transistors, and I think personally that's the coolest fucking thing ever. Excuse my language, but it's rad, dude. And yeah. Okay, as I mentioned before, you may be asking yourself, Kenny, what is a logic gate? I don't know. I at first I didn't know. A bunch of little lines drawn to make these cool little shapes. But yeah, this is covered in discrete math for computing, depending on who you take. You may have to do design and implement circuits. It's also if you're a CE or CED minor, you cover this. But like I said, how does one take a bunch of ones and zeros and ons and offs and make math happen, right? Logic gates. Picture this. I hand you. No, hold on. Let me pick one. Let's pick one. Casey, what are you feeling? What are you feeling like right now? That's too complicated to explain. Yeah. Oh, that's so simple. Oh, I'm so happy you picked that one. So picture this. You're an OR gate. I hand you a 1. Another guy hands you a 1. What's the output, Casey? Either or. Am I tripping? Oh, it is. Goodness gracious, I am. The truth table's on the thing. Oh my God. You're so right. You're so right. Okay, but anyway, it's so true, girly. Yeah, no. Me when I forget the basics of it. Anyway, yeah, it is a 1. It is a 1. It's because it's either or, and when it's both, it passes out the 1. Now, when it's none, it's 0. Hence why you pick XOR, because that would be the inverse of it in what I just explained. Thank you, Casey. I get up here, I start fumbling, and I get nervous and jittery like I haven't presented a million times. Anyway, like I was saying, though, you build these logic gates using transistors, and with these logic gates, you're able to do computations. They take inputs, and based on the state of the gate itself, or a combination of gates, you get an output. And you can do really cool math with this, right? I like this because I remember back in my Minecraft days, I used to build this, and like I don't remember because I would copy it off of Google. But yeah, everybody's still following. Everybody understands what a logic gate is now. I would assume you knew what it was before, but this is my very brief touching on it. Okay, I'm making this fun. You guys need to give me like feedback, dude. I'm sorry, because this would get really boring really fast. These are the dark times. Neat. What? Because that's Malik won't let us host more Minecraft on the stack. You should talk to him about that. Anyway. Okay, continuing though. So a closer look at this, right? So like I was saying before, you're able to combine a bunch of these transistors and form these cool little things called logic gates, right? Um, and that's cool and swag and all, right? But realistically, you're not using a single AND gate. That's not how that works. You're not using a single XOR gate. Like that's not real. So what we do is we take these combinations of transistors that were turned into logic gates, and then we package them into these things called ICs or integrated circuits for our convenience, right? And here I have what is the correct term? I mean, they're 2 input AND gates, but it's a IC that contains 4 AND gates in it. And this is very convenient because you can go and pop this in your little solidless breadboard, and then you can do cool little AND stuff, and it's cool, it's nice, and it's packaged for convenience, right? And like I said, some can be rather simple, like the 555 timer I have pointed right there. And some can be a little more complex, like the microcontroller that I have right there. And like I was saying before, as the complexity increases, so does the level of extraction, because you don't want to recreate the wheel. If someone has a package that does a certain thing, you don't want to have to recreate it. So we just have a little black box. We pop our black box into our new hardware implementation. So as you can see, I'll start going through the layers, right? So like I was saying before, this is a 555 timer, the same thing as mentioned in this schematic, but it's a nice little cute package, right? You're like, oh, I know there's a ground pin, and I know 2 of those are the input for one, the AND gates, and 2 are for the other, and there's output. It's cool, right? Look a little closer, right? This block diagram, right? Like I was saying before, though, there's a layer of abstraction in there, right? We just have the gates there. It's kind of got blurry when I blew it up, but I think there's like a dude that got blurry. I digress though, but it's a block diagram. And as it keeps going, it gets a little more complex, and we get to this, right, where it's literally the package opened up, and you can see the die, and you can see where the bond wires connect and lead out to the pins, and this is all the sea of transistors and stuff, right? It's cool. But looking at this in some kind of documentation, it's not going to help you. Hence why we have the this, right? And this is why I was saying I don't want to bore you, because no one can just look at this and think, oh, this is a 555 timer. But yeah, now you guys understand ICs and block diagrams, right? Or is everybody following along? Are we good? Okay, that's swag, man. I'm happy. But what if we need a little more computing power, right? We don't just need a little 555 timer that just does a little clock sequence for us, right? Although clock cycles are important, we might need a little more computing power, right? Boom, microcontrollers, right? So a microcontroller is a single little package that generally is used for a specific application, is limited to performing a certain set of tasks, right? They're cheap to manufacture. They're cheap to purchase. You don't need all of the fancy bells and whistles that are found in your little, I don't know, Asus gaming laptop, because this is meant for a specific purpose, and it doesn't need to do all that. It has the same components in its own way, very small scale, but it doesn't need to do all that. And like I wanted to put this here because the term high performance is relative to the application of whatever device you're using, right? Like if you're doing like a simple little like counting from 1 to 10, a Raspberry Pi is overkill, right? But you're not going to throw a Raspberry Pi into a supercomputer cluster that's used for some crazy like math, like breaking like, I don't know, some encryption algorithm. I'm not going to name any, but you know. But yeah, like I said, there's many different packages for different uses. Normally, I kind of put the Arduino here because people are like, oh, that's a microcontroller. No, it's a development board that's connected to the microcontroller, right? The microcontroller is that little tiny little dip package right there, and all the pinouts are the outputs, making it easy for you to use. But yeah, does everybody know what a microcontroller is? You guys get to give me feedback, dude. Like I'm trying, man. I'm trying. Yes. That's tough. That's tough. That's swag. But like I was saying though, these little tiny guys, these little tiny packages have all the same components as your standard little gaming computer that you're familiar with, right? We have the RAM, we have the internal power supply regulator, i.e. your power supply. You're going to interact? Yeah, what's up?
I see microcontroller, but I also see microprocessor.
What's the difference? I actually don't know. I actually don't know. Well, I do know. My controller has all the components within. So it's the flash, it's the power regulation, it's all the ALU, so the algorithm logic, whatever, in the sea of gates, and the clock. Whereas from my understanding, the microprocessor is the processor alone. All the components that are found within this controller itself are external. So you would have external flash, external power regulation, external clock, and generally, when you're in applications where you want it to be a lot more customizable, like a lot of ARM boards that are on certain devices, right? You're not going to have all that crammed inside of one package. You're going to have them spread out, and each one, like I said, not reinventing the wheel. If you can get this part from this company, it's more reliable than company B. You know what I mean? You're going to do that. It's a lot more swappable. So, did I answer your question, Braden? What's the difference between a microcontroller and microprocessor? Yeah, swag. Okay. Well, like I was saying, microcontrollers are pretty much just, excuse me, smaller computers. What time is it? Oh, we're doing great, dude. We're doing swell. Yeah, they're just computers in a package. And you can see, I wanted to put this on here because not a lot of people ever get to see this stuff. You just see this little black chip with pins coming out. But this is like the actual microcontroller, and you can see the bond wires going out to the various pins, and it's pretty cool. And I have story time afterwards about what happens when you overvolt a microcontroller. Nothing good. Bond wires melting internally. Oh, that's fun. But like I was saying, this is like the microcontroller. The image of the die. I used to be really good at part identification. I probably could do it now, but like you look at this and you're like, what in the world? And this is the actual controller. This is the die that's within this microcontroller right here. And it's really cool and really swag. I used this image specifically, or I used a different one, because I wanted to touch briefly on like how these are actually done, because this is like at like a microscopic and nanoscopic scale, which is really interesting, right? you don't really have a good concept of this, but they quite literally have to use this thing called scanning electron microscopes, where they hit the surface of the die with a laser, and the photons bouncing back are then captured. Hence why this has a red tint to it, which is really cool. And it's done at such a small scale, and it's just the coolest thing to me. Yes.
So you're telling me there's a literal die in the chip?
No. When I say die is just the term used to reference like that component, the die of the thing. I don't know where that term came from actually. That's a good question. I'm going to look into that, Chase K. Keep going though. Also, I want to touch briefly on FPGAs because we're talking about microcontrollers and where you were programming these devices, right? It's the program is stored in the memory, and the memory gets passed into all the cool logic gates and transistors or whatever. But I also wanted to touch briefly on FPGAs, like I said. FPGAs are reprogrammable integrated circuits that contain a large array of programmable logical blocks, right? This means they're flexible, they're high speed and reliable, and it's this thing called parallelism, right? Where data doesn't have to transfer or go through all these components within a microcontroller, because this device, the logic is literally implemented on the transistors. The thing can only do one thing, and it does it very well in sequential order, parallel. Different processing operations don't have to compete for resources. Like, what I was saying with the microcontroller and timing, it's still just a computer, and the processes still have to fight for time slices on the actual processing unit, the ALU or whatever, right? With this, that doesn't happen because the device is programmed to do one thing, and it goes in that order every single time. So you'll find FPGAs on a lot of applications where real-time processing is very important. That's bad. It's very important, i.e. like RF demodulators and stuff like that, where the time that it takes to complete an operation is extremely important, and it needs to be reliable. Yeah, but it's comprised of programmable interconnects, I/O blocks, and logic blocks, and the logic blocks control the logic that's implemented on the interconnects, and it's a whole bunch of cool stuff that's not in the scope of this presentation, but like I could probably talk for a very long time about this stuff. You guys should get a minor in computer engineering. Cliver does an excellent job of doing this. Yeah. So you may be asking yourself, all these transistors that do all these cool computations and implement these cool logic gates, but how does this little guy remember, right? In our case, right, it's this thing called double EEPROM. And that was highlighted in the previous thingy, but it's electronically erasable programmable read-only memory. It's non-volatile. It holds normally small amounts of data that can be written and erased in very precise increments, so at like blocks. When I explain Flash, you'll understand why I'm saying this. And yeah, it's non-volatile memory that you can erase individual segments of, and it's really cool. And I put limited time on this Earth because it's something that I found out this summer. Due to the way that transistors are in a bunch of physics, you can only write to these blocks, like depending on the device, like 100 million times. They can only handle 100 million writes or whatever, because after that time, the transistors stop holding a charge. If it won't hold a charge, I believe the charge will drift and it'll hold data, and then just kind of data just like evaporate away. Which is really interesting because you never really think about the life cycle of like the microcontroller in your phone. Like what happens when you can't write to this thing anymore? It's very interesting. And then I go into Flash, yeah. Just writing, because you're modifying the charges held within the transistor. I'm not sure about read operations, but I know for a fact it's writing. But like I was saying before, double EEPROM only holds a small amount of data, just due to the nature, or due to rather the structure of double EEPROM, right? When you want larger amounts of storage and like high density, right, you move into Flash, which is also non-volatile and also can be actually erased and reprogrammed. However, when you're interacting with Flash, you don't interact with the individual gates. You interact with these things called pages, right? Like I was saying before, I'm going to point at the board now. With double EEPROM, you're indexing these individual gates, right? With Flash, you do the entire page as a grouping. So normally, from my understanding, double EEPROM would like hold critical information about like boot or the CPU starting up, right? Whereas Flash would hold the actual program code. So double EEPROM point tells the CPU to then look at Flash to load the actual firmware. So it's like a kind of in-between step. They're used for different purposes. Yeah, I have a D flip-flop on here because, is it snowing? Oh my goodness. I have a D flip-flop on here because you may be asking, how do registers hold their state, or how do you hold data after like clock cycles pass and you would implement a flip-flop? And there's other types of flip-flops, so D, RS, Q, other stuff. Yeah, and these are just AND gates that are taught to hold data and hold values after clock cycles. Pretty cool stuff. Kind of talking in circles now, so I'm gonna keep going. Does everybody understand what flash memory is, right? And indexing like pages, which are just groups of gates that hold data. Okay, we're good. Let's go. Swag. So maybe asking yourself, Kenny, where are these little guys used? And they're used everywhere because, like I said, they're cheap to make. They do their job well. And yeah, like they're in toys, they're in thermostats, they're in refrigerators, they're in whatever this little guy is. I'm pretty sure some kind of like orientation sensor integrated in there. But yeah, they're just really cool. You once you realize like what these things are, you start seeing them in everywhere. Like they're in the door locks, and they're in the lights, and they're in the projectors, and it's just cool stuff that you notice. Hold up. Yes. Yes, and I'll get into that later. We're traversing the terrain right now. I'm trying to give you the precursor knowledge of so when we get to that part, you guys know what I'm talking about. Like I said, really, what are these things used for, right? I didn't cover like the different architectures used, but these things are used everywhere. Ironically, the microcontroller, the ARM chip that, well, the microcontroller board specifically that we were using in ARM assembly, no, what is it? C and assembly for embedded devices in class is actually used on the Starlink satellites. And it's just cool because like these things, you can't send a conventional computer up there to do this stuff, right? It needs to be quote unquote bulletproof. It needs to be tough in environments where the conditions aren't so good. So you end up finding these things in crazy devices, right? So everything from drones and satellites. That image is actually a missile. But yeah, it's just cool stuff. But yeah, it's like these things are so practical, right? And you just never know where they're at. Like these things are everywhere, dude. And yeah. So what you really came for, right? They ask me. Yeah. This be used offensively. Oh, Let me tell you something. Picture this. Yeah. We're gonna keep going. Hardware hacking methods and techniques, right? This is where I'm about to start rambling, and it's gonna get really fun. So right now I'm gonna, go over component IDing in data sheets, serial debug pins and pin fuzzing, inducing fault injection, right? Side channel attacks briefly, and laser attacks will probably be covered in fault injection because technically it is inducing a fault. Yeah. So one of the most important steps to actually like understanding how a device works and quote unquote hacking it is pretty much doing part ID. Like I said on here, in order to break something, you need to know how. You need to know what it is, right? You can't just be like, oh, this little like, I don't know, flash drive that is quote unquote secure, I hack it, and that's not how that works. So you really should take your time to attempt at least to identify the components on the device, and you need to ask yourself, what is the application of this device, right? Like, I don't know, like your kid's toy is not going to have a TPM module on it. There's no need for that. So why would you think that part's on there, right? Max Fusco's laptop will not have a TPM chip on it. Braden says, okay. Yeah, and it's like, who makes this device, right? Um, Depending on the manufacturer, you kind of have a good idea of the chips they use inside their parts. Like what Apple devices having Samsung chips in them, it's like a whole thing. It's kind of funny. Yeah. What are the onboard microcontrollers and ICs? Is there any onboard storage or external storage? Any potential programming pins that you can actually tap onto directly on the microcontroller? UART and JTAG interfaces. I think no. I'll talk about that briefly. Do you guys want to know what UART and JTAG are? I probably should go into that. I'll go into it later. And I/O ports. Normally you could find these sweet data sheets that contain all the information you need about the parts. And that's pretty cool. That's pretty cool. So picture this. You get a device. All the labels on the chips are wiped off. There are a bunch of random contacts on the board that you don't know what they do. And there's no documentation because it's pretty much a black box. But so there's techniques to get around this, right? Generally, you can actually attach logic analyzers to the devices and turn them on and see what those pins are doing and what those pins are reading. What I oftentimes found myself doing was just finding similar parts. If there is no data sheet specific to this controller or whatever, right? This manufacturer may have a similar part because, like I said, people in the hardware space don't like reinventing the wheel. It takes so long to stand up a foundry, excuse me. It takes a lot of money. Forgery? Yeah, no, foundry, I'm sorry. It takes a lot of money to develop this stuff. Like, it's cheap when you're manufacturing like 1 million of these or 2 million of these, but like at a small scale, no one's gonna be reusing this stuff, right? So a lot of the commands and actual implementations on chips are kind of reused, and you'll see that when you really get into this stuff. What was I about to say? Yeah, logic analyzers, I found myself doing that a bit, where I didn't actually know how to interact with the device. So you attach it to a device that does, and then you take your little guy, your Cellier, and you attach on, and then you're able to see the device interacting with another device, and you're able to reverse engineer that and develop your own little communication protocol for that. So it's pretty swag. Yeah. Finding debug ports. There's these things called JTAG and UART. So JTAG is a standard. It's not actually an acronym. It's like the acronym for like Joint Task Force or some crap. It's actually covered in me and Emmanuel's hardware hacking presentation from last spring semester. So if you want to go watch that, go watch that. But UART, the Universal Asynchronous Receive and Transfer protocol, it's used for doing serial communication between devices similar to JTAG. There are a bunch of other protocols like I2C and SPI, and these are serial communication protocols that are used normally. There's normally contacts for those on parts too, but it's just identifying what the parts use and what the device use. And like I said, normally you can find this in data sheets, but sometimes you have to guess. And there are devices that help with this guessing. And it's pretty much pin fuzzing. Similar to how you would develop a fuzzing harness and fuzzing application, you can actually do hardware fuzzing where you just try a bunch of combinations on known good pins and see what happens. And yeah, it's pretty swag. Yeah, I put this on here because, like I said, X-rays are really nice to have when you're doing hardware reverse engineering. You're actually able to X-ray the device and see the different layers within the PCB and then do a little bit of a circuit tracing. And you can see, oh, pin right here, pin right here, pin right here, and pin right here connect conveniently to the programming pins on the controller. Interesting. Interesting. I wonder what those pins do. And yeah, we don't have X-rays, but X-rays are nice. And if you ever get the chance to use one, use it. They're pretty cool. Ops budget. Thoughts, Malik?
Yeah, absolutely.
Malik says absolutely. Any questions? Please ask me questions. This needs to be fun. No questions? Really? Wow. Mackenzie? Well, I've only taken one at RIT, and it's the C and assembly class, and it was pretty swag. I don't like lab reports, though. Yeah.
When you deal with obfuscated devices, do you have like a step-by-step process of what you try?
Based off what I've done and what I've seen my old people do, it kind of is. It's like the initial like disassembly and part identification. Then from there, you kind of assess what tech factors you want to use. Generally, the first doesn't work. and the third doesn't work, and then you end up moving to the fourth, and it's kind of just trial and error based off, like I said, don't reinvent the wheel. If you know this part is susceptible to this attack, then do that. And if a family part is susceptible, then do it. I kind of wanted to touch briefly. Actually, I'll do it later. I'll continue. Any more? I think there's another one over here. Okay, I digress. This presentation is all over the place, but that's how I like it. So closer look at this, right? Like I mentioned before, me and Emmanuel did this funny little thing with a funny little camera where we abused the JTAG connectors on it and got a root shell in the end, and it was pretty cool because you could dump firmware from JTAG depending on the device. And yeah, baby. And yeah, no, this is the upper picture. I believe is some kind of, I don't know, but the EMI shield's ripped off, and it looks like they're tapped onto UART pins or JTAG pins because it's 10 connectors, I believe. And this literally is what it looks like, dude. It's just tapping onto these random connectors and getting a shell on these things because they don't secure them. There's also an X-ray up here, and you can kind of see, I think it's what is the package, QBF. The pins are underneath the package, and yeah, this is what it looks like when you X-ray a PCB. And yeah. So fault injection, right? People want to know. People want to know what are some methods and techniques you can do. So basically, fault injection is essentially inducing stressful or abnormal conditions on a computing system. You design this part, you spend all these months designing this part, and you don't take into account what happens when you do an oopsie on the part. It can't handle the oopsie, right? So there's these things called timing fault injections where you actually glitch the incoming clock signal going to a specified part. So if a part relies on there being consistent pulses to keep track of what's happening, and you say, we're going to skip through, and it's and then you're able to yank, I don't know, keys out of certain security modules, and it's pretty cool. Yeah, personally, I've never done this one, but it's pretty swag. The next one would be voltage injection. So picture this again. This part requires 5 volts. What happens if I give it 2.7?
Homemade LEDs.
It doesn't work properly. And you're able to skip certain security verification steps because it doesn't have enough power to do that step. I've done this one, pretty swagger. There's this thing called, what is the tool called? It's called the chip whisperer. And it's this little external microcontroller that's used to induce effects on other microcontrollers, and it's really cool. Again, electromagnetic fault injection. You take a part and you start spamming it with electromagnetic pulses externally, and the part's and then it gives you what you want, and it's great. It's great. And then the fourth one that I can speak on would be the optical fault injection, where pretty much some more physics. If you smack transistors with certain wavelengths of light, they get a little grumpy, and you're pretty much able to say this transistor has a value of 1. It's now 0 because I smacked it with the laser. It's pretty cool, pretty tough. It goes back, I will go back later, but in one of the diagrams, in one of the die images, there's things called lock bits, and normally these lock bits are set so that you can't read back firmware once it's on a chip. And you can do certain things with that. I'm not going to go into detail, but yeah, you're able to quite literally flip bits with light. Expensive, but you can do it. But yeah, any questions on any of these attacks? Please ask me questions. This is getting very sad. Chase K, yes. Which one's my favorite? Whatever gets the job done. Yes, Devin. Yes, you are. So you remember what I was saying, Brayden asked me the question about difference between microcontrollers and microprocessors. Generally, microprocessors take external clock signals from some other designated thing that does the timing. What happens when I remove that timing implementation and I supply my own? Yeah, what you'll notice is a lot of this hardware stuff you actually need to be hands-on for it. I'll cover it in the next slide, but yeah, most of the stuff you actually need hands-on access to. It's really good to have a device that you can rip apart and actually understand it prior to actually attacking your attack part. Yeah. Side channel attacks. This is where it starts getting a little goofy, silly. You know what I mean? So a side channel attack is pretty much an exploit that aims to gain or gather further information from influencing external conditions, um, or exploiting things that indirectly affect the system, right? So some of these include electromagnetic side channel attacks, which is pretty much capturing and viewing the um, leakage of electromagnetic energy. Acoustic, so audio signs. Power, actually monitoring the power that or chip, the power of a chip's, the consumed power of a chip that hey, the consumed power goes up by 0.3 3 seconds in the boot process. I wonder what's drawing that, and then you're able to understand, oh, maybe there are some checks that go on that need a little bit extra power. What happens if I dip the voltage down? Did the checks still go through and pass? And you see this kind of step-by-step thought process when doing this. Row hammer, right, is when it's an attack. I guess it's considered a side channel, but it's pretty much smacking the rows around the page that you actually want to attack. And it's able to indirectly influence the middle row and then flip bits. So then you may be able to read. You remember I was referring to the pages in Flash earlier and how they're not individually addressed, they're addressing, this is an application of that where you're repeatedly reading and writing to the rows surrounding the row that you actually want. And you're able to modify that row by the surrounding rows because of physics. And yeah, cold boot attack, this is one of the silly, goofy ones. Pretty much, you guys understand the concept of volatile memory, right? RAM. If you don't, it's temporary memory. You write to it, and when the device is powered off, you lose that. It's not non-volatile. What time is it? Okay, I'm good. So picture this. Picture this, right? You have a device that has contents in the memory, and you're not able to directly access the memory within this device for reasons like, oh, the computer's locked and I'm not able to actually touch the device. You super cool the memory array with a chilling agent of your choice. In this case, they're literally just using compressed air. You freeze this, drop the temperature down real quick. You yank the RAM chip out after the device is powered off. You put it in your actual forensic system and you read off the memory. Because physics, right? Because that's totally how that works. And it's cool. It's cool. I can't explain it further than that, but it's cool. And yeah, swag. DPM. So yeah, Michael Vaughn had told me, and I think I should have done it, and I did. I should kind of briefly touch on DPM because this is a real life implication of like an actual hardware device that you guys will be interacting with because Windows 11 requires it, and a lot of things are now requiring TPM as an external hardware security validation device. And it's designed to perform hardware-based security-related functionality, right? And then they generate, store, and limit the use of cryptographic keys and your desired application. And it's used for authentication because there's a RSA key that's actually burned onto these devices that you cannot modify. There is a thing, what is the actual term for it? But pretty much there's transistors that you can only write to once. And once those are written that way, you can only read from it. You cannot rewrite those. Unless... Yeah, ROM. Thank you. Read-only memory. Thank you, Max. I get up here and start stumbling on my words, man. ROMs. Okay. Used to ensure platform integrity by taking and storing security measurements of boot processes. Hence why I was saying it's a new requirement in the Windows 11 to implement whatever security mechanisms they are doing. Recently, as of like last week, there's actually an exploit. It's an integer overflow for TPM 2.0 where you're able to actually overflow into the space where keys are stored and like arbitrarily just read and write those. So, so-called security mechanisms are not very secure, and I hope you guys understand that after this presentation. Unfortunately, there are no demos because I don't have the devices to actually show you voltage glitching or laser attacks because that's expensive, and we need lab space. And I don't have hydrochloric acid to decap microcontrollers, so yeah. Questions? If you know where this is from. Questions? Please ask me questions. We have time. I actually filled up my allotted time by rambling. Did you guys learn anything? Please tell me you did. I tried to stay very high level because you can get into the weeds of this really fast, and it's not fun, and I will put you to sleep. Yes. Oh, okay. Dude, please ask me questions. Okay, Alex. Did we find so in this image specifically, it was not Michael Vaughn's laptop that was the targeted device. It was my laptop. I we went to UB and I was very sleepy that day and I left my MacBook at UB and we went out and we came back like 5 minutes later and Voss we just took my laptop and we're like, where is his laptop? Where is his laptop? And we end up figuring out that Vasu has my laptop because his thought process was, oh, I'm going to come to Rochester tomorrow and drop it off. Okay, buddy. He then proceeds to send us this text. And he's like, meet me at the back of a gas station. And now I am 98% sure there are some aftermarket Vasu edition hardware security chips installed in my MacBook. Yeah. Yeah. Okay, any more questions about hardware stuff, please ask me, yes. It's almost like they did that. Hmm. Mm. Interesting. A certain, what was it? It was Asus a few years back. Was it Asus or Acer? It was some laptop manufacturer that did a certain thing, abusing certain hardware chips, certain back doors, certain boot kits. Anyway, any more questions? Please ask me questions. Yes, Chase K. I'm sorry, Sohail. Fiddling stories, yeah. I can tell you about oh, when we burnt bond wires, dude. Yeah. So, I'm gonna stop recording now. Goodbye, stream. It's the end. We're gonna go over to research very soon. I'm gonna tell some stories off camera. But yeah, I hope you guys learned something. I'm not an engineer, by the way. I just do this for fun sometimes. And yeah, um, goodbye.